By the year 2041, the silicon that powers your phone, your car, basically the entire modern world, is actually scheduled to vanish.
Yeah, it's really wild to think about.
Right. So welcome to today's deep dive. Our mission here is to figure out what on earth is going to replace it.
And, that disappearance is completely driven by physics. I mean, for 60 years, the industry's golden rule has basically just been to make transistors smaller.
Smaller and smaller, yeah.
Exactly. But as those electrical pathways shrink down to the dimensions of individual atoms, well, nature just stops cooperating. We hit this massive wall called quantum tunneling.
Wait, quantum tunneling. So that's not just a leak, right? I mean, it's more like throwing a tennis ball at a solid brick wall, and instead of bouncing back, the ball just magically materializes on the other side.
Yeah, exactly like that.
Like the electrons are literally teleporting through the barriers that are meant to stop them.
Right, and that teleportation is what breaks the transistor. If electrons are acting like waves and they just phase through the walls, you can't turn the switch off.
Which is a huge problem.
It's a deal breaker. So if silicon can't hold these electrons back, we have to find a completely new material that actually can, and enter molybdenum disulfide, or MOS2.
MOS2.
Yeah.
Which is this 2D semiconductor naturally just 3 atoms thick, right? Like one molybdenum layer sandwiched between 2 sulfur layers.
Yep, exactly 3 atoms.
But how does being incredibly thin stop the teleporting tennis balls? I mean, it's like trying to squeeze water through a microscopic hose that keeps leaking. Does starting with a perfectly flat 3-atom hose magically fix the leak?
Well, it really comes down to electrostatic control. So think of the transistors gate, the part controlling the flow of electricity, like a magnet trying to control iron filings.
Okay, tracking so far.
Right. So in chunky traditional silicon, the actual physical pathway the electrons travel through is relatively thick.
Right.
That means the magnet is too far away from the electrons at the bottom of the pathway to effectively control them.
Ah, I see. So because MOS2 is only 3 atoms thick, the gate is intimately close to every single electron in that channel.
Exactly. It gives the gate total leak-proof authority. And because it starts out incredibly flat, unlike silicon, which, has to be whittled down pretty messily, there's no atomic chaos for the electrons to navigate.
Wow. And that absolute control fundamentally changes the power dynamic, doesn't it? Because the gate has such a tight grip, it requires significantly lower voltage to operate.
Oh, absolutely. We're talking up to 1,000 times less energy than comparable silicon devices.
1,000 times. Wait, really?
Yeah, which is a massive lifeline. I mean, when we talk about the AI energy crisis, we aren't just talking about abstract server farm.
Right, we're talking about the power required every single time you ask an AI a question or generate an image.
Exactly. If the industry doesn't get drastically more computing per watt, your digital life hits a literal power wall.
And the crazy thing is, this is already moving out of the lab. Like, a processor in China was recently built using 6,000 of these atomically thin MOS2 transistors with a 99% yield, meaning almost every single one worked perfectly.
Which is huge.
But, 6,000? I have to push back here a little bit. Modern GPUs have over 300 billion transistors.
Right, yeah, it sounds small.
So 6,000 sounds like we're just hitting the reset button on computing. Is that disappointing?
Well, think back to the legendary Intel 4004 chip. That was the first true microprocessor, and it only had 2,300 transistors.
Oh, wow. Okay.
Yeah, so getting 6,000 atomically thin MOS2 transistors to work together on a single chip without defects, that is a monumental proof of concept for this new era. The trick now is really just scaling it up for mass production.
Because building one perfect chip is vastly different from printing billions of them.
Exactly. And the primary enemy in industrial manufacturing here is what we call grain boundaries.
Gray boundaries.
Yeah, so as you grow these 2D materials, tiny crystals form, they collide, and they create microscopic cracks. So growing perfect large-scale sheets is notoriously difficult.
Right.
But a company named C-Dimension is solving this by flowing gases over a wafer to slowly assemble the atoms at a remarkably low temperature of about 200 degrees Celsius.
Okay, wait, let me make sure I'm tracking here. 200 degrees is low. Normally, traditional manufacturing blasts materials at nearly 1,000 degrees, right?
Right, much hotter.
So if they do this at 200 degrees, it wouldn't melt any existing silicon transistors sitting underneath it.
And that's the crucial mechanism right there, because the goal isn't actually to completely scrap silicon overnight, it's to build directly on top of it.
Oh, I see.
Yeah, so dropping the temperature unlocks monolithic 3D computing. You just stack layers of 2D logic directly over the old silicon foundations.
Oh, wow. Okay, so basically because we ran out of flat land for our silicon suburbs, This low-temperature trick finally lets us build vertical skyscrapers of data.
That's a perfect way to picture it, honestly. But, this architectural shift will take time.
Right.
You'll likely see these 2D materials show up in smaller applications first, like 6G networks or photonics.
Photonics, where we compute using light instead of electricity.
Exactly. You'll see it there long before it becomes the main engine in your laptop.
It's a total paradigm shift. Which really brings us back to that vanishing silicon and our new blueprint.
Definitely.
So, if the future of computing requires building microscopic 3D monolithic skyscrapers, how will that extreme vertical architecture completely change the physical shape, design, and cooling needs of every single piece of technology you own?
That is the big question.
Definitely something for you to ponder. Thanks for joining us on this deep dive.